Okay, so to reiterate for those watching at home, the worksheets we did on Monday and over the weekend, that is the stuff that'll be on the quiz on block day, Wednesday and Thursday of this week. This new material we will be doing some practice with. For seniors, this new material will be on your final on Monday. I will give you some individual practice and give you time to come in and go over it. All right, we are still dealing with stoichiometry, or the quantitative relationship between things in a chemical reaction. The first concept we're going to deal with today is called percent yield. Okay? All right, this first page, you do not need to write stuff down for this first page. These are things to think about or talk about. First of all, remember percent, no matter what you're talking about, means per 100. Okay? Anytime you deal with these kind of problems, you're going to get a ratio and then multiply it by 100. All right? If you ever see something where they talk about parts per billion or parts per million, you do it the same way, but instead of multiplying by 100, you multiply by 1 million or 1 billion, because it's a very, 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 very slight effect. Does that make sense? All right? If we're looking at side effects, you want it to be in the parts per billion. You don't want per one, the side effect of this will make you grow a third eye about 5% of the time. That would be horrible. We would never allow that. But if it causes you to have some kind of, maybe it causes a rash in 1 out of 1 million, that's probably a side effect we can live with if it has better benefits. Does that make sense? So that's the difference, all right? Okay. In the stoichiometry calculation we've been doing so far, we are assuming that they go completely, right? Like when I talked about it with combustion, we're going to assume it's complete combustion, all those kind of things. All right. What that means is we would get a 100% yield. Okay. Now think about making cookies. If you look at a recipe, maybe it says that this recipe yields 5 dozen cookies. All right. If you've ever made cookies before, do you ever get the exact amount that it says it's going to make? No. In my household, you have to pay the toll of me stealing cookie dough out of the bowl before it ever makes it to the oven. All right? Because I like cookie dough. My wife gets mad. There's raw eggs in there. Okay. Still tastes delicious. All right. I know it's bad for you. I'm okay. All right. Now, in chemistry world, as you start creating stuff, the new product starts blocking the reactant sometimes from getting together and making more product. All right? Iron rust, and then it breaks off and more rust, and then it breaks off and more rust. All right? Aluminum, everybody thinks aluminum doesn't rust, but it actually rusts really, really fast and creates a layer of aluminum oxide on the outside that prevents the oxygen from getting to the inside and rusting through. Okay? We don't call it rust, we call it oxidation, but aluminum actually protects itself. Same thing with copper. If you ever see copper, some old buildings have copper gutters. When they first put them on, they're bright, shiny copper colored, and then they form, we call it a patina, but they turn green. It's a type of corrosion that actually protects the copper underneath. The Statue of Liberty, as I understand it, originally was copper colored, and then it oxidized, or it corroded, and that's why the Statue of Liberty is green. I would have loved to have seen it when it was copper colored, and of course, no color photography back then, so, All right, now, for chemistry, here is the definition you need to write down for percent yield, okay? Percent yield is the ratio of the actual amount produced to the theoretical or calculated amount. This theoretical is what we get from our stoichiometry. All right? We get the theoretical from our stoichiometry. Are you with me? All right, so that is our definition. In industry, we try to maximize the percent yield, right? They don't want to have to waste their raw materials, so they want the most they can get. We talk about that a lot of times in terms of efficiency, right? Automobiles are not very efficient. The energy that goes from the gasoline that goes to making the cars move is probably well below 50%. A lot of it gets wasted as heat energy, right? It heats up the engine, heats up the environment, blah, 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 right? It's not going to make us move, okay? That's why in terms of efficiency, the electric cars are much more efficient because you're not wasting as much fuel on other things. Even the noise that a gasoline engine, that's part of the energy going, that's not making the car go forward, all right? So, percent yield. As I understand it, this is one of the things that like a chemical engineer would work on. You know, they're working on new materials, working on this, and then they also work on the processes to maximize the efficiency of the plant, get the highest percent yield for the lowest amount of energy you have to put into it and stuff like that. Does that make sense? That's my understanding. I'm not a chemical engineer. I just have a degree in chemistry, not engineering. Okay? All right. How do we get percent yield? Okay? You take the actual amount. That's going to have to be given to you in the problem. If we had time, we'd do the lab. I actually have a kind of a fun percent yield lab. We'd do the lab and we'd be able to calculate it out. But it's what we get either from lab or from industry. Okay? A lot of times, one of the areas where they talk about yield are farmers. They talk about their crop yield in bushels and stuff like that, yield per acre and stuff like that. You know, and they get a baseline, and then that's if they either get above or below that. That's kind of how they do their percent yield. You know, they have an average is their theoretical amount, and in bad years are below average, and good years they get above average. Okay. Generally in chemistry, you should not ever get over 100% yield. If you do, you probably had contamination in your product. And that's something to be important to take care of, study. There was a really bad process where they weren't keeping track of this. It was actually a US company in India. And then once they figured out they had a major problem, the executives left, the plant exploded and let out toxic material and killed over 20,000 people. And then people go, I wonder why they don't like us. In that case, I think eventually those executives did get prosecuted, which is good, but that doesn't always happen. So anyway, yeah, it was a really bad deal. So anyway, that's major reason why we want to keep track of our percent yield. And the other is if you're a company, you're wanting to maximize your profits, right? You don't want to waste stuff. Okay? So, like we talked about with stoichiometry, remember I always had you write down your given and your what you want. Okay? When we're doing percent yield with stoichiometry, we want to have our actual, which will be given, and our theoretical. Okay? So theo. All right? They could give you both. Oh, sorry. Scrolling up. They could give us both of these. Most of the time, and like on the final and stuff, they will give you your actual. They always have to give you the actual, and you'll have to calculate your theoretical using your stoichiometry, okay? So for percent yield, when you see something talking about percent yield, you're going to want to write down those two things, all right? Keep your work organized. Are you with me? Okay, you ready to do one more thing that we can do with percent yield. There are processes where we know what the percent yield's going to be. Again, that's one of the things that they try to maximize. And they know, hey, in this process, I always get 85% yield, or that's my goal. All right. If you know that, what you can do is take your theoretical amount times the decimal for your percent yield. So basically, you take the percent, divide it back by 100, and then you multiply it by your theoretical, and that'll tell you your actual amount you should get. All right. So again, like if we have 85% yield, the decimal would be 0.85. If that's confusing to you, just multiply it by the 85 and divide by 100. Okay? All right. And like I said, we're going to do practice on this before the final, definitely. All right? But remember, these kind of questions we're doing today will not be on tomorrow's quiz. The stoichiometry part will be, but these questions will not be. All right? Okay. Ready to go on? Okay. All right, we're going to look at this equation. There's a lot there. Don't bother writing it down like we did the other day. We'll just keep referring back to it. So 2 FePO4 plus 3 Na2SO4 yields Fe2SO4 plus 2 Na3PO4. Okay? So we start out with a normal stoichiometry problem. It tells us we have 25 grams of iron 3 phosphate. How many grams of iron 3 sulfate can we make? Okay, up here, which one's iron 3 phosphate? The FePO4. So our given is 25 grams FePO4. Okay, what do we want? Grams of iron 3 sulfate, which one's that? Yeah, the Fe2 parentheses SO4 parentheses 3. Okay, and that's important because that's going to change its molar mass. I actually messed up when I was doing this example problem earlier and forgot to write down the 3 part there, and yeah, messed up my answer. All right, so we're going to do the stoichiometry just like we've done before. Remember, the stoichiometry has 3 steps. Oops, I was holding up 4. Has 3 steps. What's the first step in stoichiometry? Yeah, well, okay, yeah, we're going to write the given. And then what are we going to convert the given to? Convert the givens to moles. All right, so if I have grams on top on this first step, where does it go? Or if I have grams on top to begin with, where does it go on the first step? Bottom. All right, so grams FePO4. And what goes on top of that? What are we converting it to? So mole goes on top. How many moles of FePO4 on the first step? 1. Remember, the first step is always 1. If they give us moles, we skip the first step and go straight to the second. Now, the grams we get off the periodic table. I'm going to scroll so everybody can see. How many Fe's are there? 1. How many P's? 1. How many O's? 4. And then times their mass, 60.0. 31 for P and 55.8 for iron. So it'll be 55.8, 31, and 64. And grab our handy dandy calculadora.
Can you move your paper up a little bit?
Up? Like this?
Down. Like down.
Oh, down?
Oh, yeah. Perfect. Thank you.
You're welcome. Yep. All right, so we'll add those together. 55.8 plus 31 plus 64, and we get 150.8 grams there. We can cancel that unit if we want to, or you can wait and do that at the end. Now, is everybody with me? Caught up right now? Nope? Okay, I'll give you a minute. Okay. All right, now, the next step is the mole to mole step, right? So if I have moles FePO4 on the top here, where does it go on the next step? Bottom. All right, I'm going to scroll down. From our balanced equation, how many moles of FePO4? 2, because of the 2 as a coefficient. All right, so 2 moles FePO4. And then the moles of what we're trying to find, which in this case is Fe2SO4. How many moles of Fe2SO4? It's 1 because there's no number there. 1 mole Fe2 parentheses SO4 parentheses 3. Okay, that's step 2. All right, and we could cancel if we want to the moles FePO4 at this point. All right, oops, scroll, getting us back here. All right, and the last step is to convert to the grams of what we want. If I have moles Fe2SO4 here, where's it go on the next step? Bottom. And remember, step 1 and step 3, it's always 1 mole Fe2SO4 3. And then the grams of Fe2SO4 3 goes on top. Okay, so we have to add that up again. Fe, S, and O. How many Fe's? 2. How many S's? 3. Sorry, my handwriting's kind of hard to see up there. My tip's wearing out on my marker. All right, how many O's? 12. Good job. All right, times, 16, 32.1, and 55.8. So that's going to be 111.6, 96.3, and 12 times 16, 192. So we add that all together and we get 96.3, 111.6, 399.9. Could we round that to 400? Probably. Are we going to? No. Okay, I'm going to do the bottom first because it makes it easier for the calculator. All right, or for me for the calculator later. 150.8 times 2 will be 301.6. And then 25 times 399.9. That would have been easier to round it. You get 9,997.5. On top, take the top divided by the bottom, divided by 301.6. Oh, I didn't get the decimal point. 9,997.5 divided by 301.6 is, all right, so we get 33.1, and actually we only had 2 significant digits, so just 33 grams Fe2SO43. So if everything goes perfect in our reaction, this is how much we should theoretically produce. Are you with me? That's just the stoichiometry we've done before. Are you with me? Okay, so now we go back to our original question, and we're going to take it a little bit further. All right? If we actually end up with 18.5 grams of iron 3 sulfate, what would be our percent yield? Okay, so this is where now we're doing percent yield. We're going to write down actual and theoretical. All right, theoretical is what I just got, 33 grams Fe2SO43. And what we actually got from the information was 18.5 grams Fe2SO43. Okay, so all we have to do is take this divided by this times 100, and that will give me my percent yield. So 18.5 divided by 33 equals that times 100 equals 56% yield, or just 56%. All right, is that reasonable? Yeah, it's not great. Some chemical reactions are like that. They block what's going on. Kind of like if you ever had a little campfire, sometimes they go out, right? Some of the wood doesn't burn all the way. Or sometimes the reaction slows down so much, it's kind of like, yeah, it's not worth going anymore. I can make more money by grabbing 56%, right? And then clean out my vessel and start over. I can do it, get that 56% over and over, and I'm not taking up my reaction vessel. Yes, ma'am?
The actual and theo always have the same elements to the same.
Yeah, okay, that's a great question.
What if the
The same compound? Yeah, will the actual and theoretical always be the same compound? Yeah, it needs to be. If it's not, either one, you solved your stoichiometry for the wrong thing, or two, the problem's messed up. So anytime I'm doing them, I'm not saying I'm 100% perfect. My percent yield's not that high, but if I mess up that bad, you let me know and I will fix it for you. Yeah.
what if they're not in the same measure, like grams and one's in liters?
Oh, if they're not in the same measurement, I see what you're saying. You would want to make sure and solve it for that, so you'd have to do the stoichiometry for it. Yeah, just solve it. And if it's grams and liters, It will be for everything we're gonna do. Yeah, yeah. That's a good question. Yep. Okay. Any questions on that? That is actual and percent yield. Okay. I am going to pause this so that I'm going to make 2 videos out of this. So give me just a second to pause it and restart for the second part of stuff we're doing today. Oh.